Hello everyone. Today's class about tuned amplifiers. So what is tuned amplifier, or what do you mean tuning? So tuning is a circuit that is an AC circuit. They are LRC or RLC circuits. That circuits, it may be series circuit or parallel circuits. Thus we can call it tuning circuit. That may be in series or in parallel. C R L R L C. Thus circuits, we can call it tuning circuits. It may be in series circuit, it may be in parallel circuits. So where they apply a tuning circuits, a tuning circuit we can apply in the receivers, maybe in mobile or in radio or in television circuits. So I have a device, a radio or a mobile, in which I can listen. In that device, the speaker will work when current pass through it. We need current to pass, and the current should carry signals to which we want to listen. The signals, they are in the space and also give to me by the cable or in the space. That means maybe by wire or wireless systems. The thing is that the space, these are millions of such signals which are mean my mobile, your mobiles, for his mobile, for everybody mobile. The signal are, or the space, again, if a cable comes to that cables in my television, it carry 100 types of signals or 1,000 type of signals. One signal may be for Ethiopian Broadcast Corporation, and the other signal for Fana Broadcast Corporation, and the other for EBS signal. For this one, there are hundreds of signal coming now. I want to see signal that I do that particular signal. That's what I want in my receiver. In the space, there are so many electromotive force. So in this electromotive force, that becomes E naught sine omega of t. So our particular signal is in the omega. So that's what I want. The highest current it comes from this electromotive force. So signal around as one particular for which I want to tune to my mobile number that I can talk. Now this connection, the tune is tuning. I can get a current from all the signal, but I will choose only one. When I choose one, then I will get current from that particular signal. Let's say maybe I have the program from ABC, Ethiopian Broadcast Corporation. So the current from the APC tune I will get in my television, and that I will show starting. I don't like, I want to choose, or I want to change to FPC. So simply press my remote, so I will show starting. So I don't like, I want to change FPC, so I want to see or starting FPC TV. So the tuning with the FPC that I see in the FPC TV. So what is tuning? Connecting of the two, or what is the process of this tuning? So what today study about the tuning, that is really interested or very interested chapter. So how to get, that is a particular or resonant frequency. That resonant frequency means FR. That means that is natural frequency. At what time that resonant frequency is tuned. So this circuit, that is amplifier circuit, trans amplifier circuit, that our load is replaced by a tuned circuit, that we can call it tuned amplifier circuits. So tuned amplifiers are the amplifiers that are employed for the purpose of tuning. The tuning means selecting among a set of frequencies available. If there occurs a need to select a particular frequency while rejecting all other frequencies, such a process we can call it selection. This selection is done by using circuit called as tuned circuit. When an amplifier circuit has its load replaced by tuned circuits, such an amplifier can be called as tuned amplifier circuits. That's what I said. This is tuned amplifier circuit when our load is replaced by tuned circuits. So the tuner circuit is nothing but LC circuit, which is also called resonant or tank circuit. It selects the frequency. A tuner circuit is capable of amplifying a signal over a narrow band of frequencies that are centered at resonant frequency. So at that resonant frequency we can get particular frequency. That particular frequency, that is a natural frequency that we can hearing, you can watching different TVs. So when the reactance of inductor balance the reactance of capacitor in the tuned circuit at some frequency, such frequency can be called as resonant frequency. It's denoted by FR. So the formula for resonant is from when both XL equal to XC. So reactance of inductor equal with reactance of capacitor. So how they get this one? Let's show you. When reactance of inductor equal with reactance of capacitor, so XL means that 2 pi FL balanced with XC means 1 over 2 pi FC. So to get the natural frequency or the particular frequency or resonant frequency, let's take crisscross or let's simplify it. So 2 pi FL multiplied 2 pi FC equal to 1. So as the unity factor we get the resonant frequency. So that means 4 pi square F square LC equal to 1. So this means to find the resonant frequency, let's out F square. F square, it becomes 1 over 4 pi square LC. So F becomes the root of 1 over 4 pi square LC. So when you out from the root, 4 becomes 2, F becomes 2, and pi square means pi under root of LC over 1. So resonant frequency means 1 over 2 pi root of LC. This is our natural frequency or resonant frequency. During what? During when reactance of inductor balanced with reactance of capacitor. That means in the unity factor we get a resonant frequency. So a tuned circuit can be series tuned circuit, series resonant circuit, or parallel tuned circuit, parallel resonant circuit, according to the type of its connection to the main circuits. So when you say about series tuned circuit, the inductor and capacitor connected in series make series tuned circuit as shown in the following circuit. So this is LC circuit in series. So during this series circuit, resonance circuit offers low impedance which allow high current through it. A series resonance circuit offers increasingly high impedance to the frequencies from the resonant frequency. But during in parallel, the inductor and capacitor connected in parallel make a parallel tuning circuit as shown in the figure. So LC circuit side to side, that is parallel tuned circuit. So during this time, the resonance circuit offers high impedance which does not allow high current through it. A parallel resonance circuit offers increasingly low impedance to the frequencies from the resonant frequencies. So let's see, analyze from the two types of tuning circuit. One of them is parallel tuning circuit. How they analyze a parallel tuning circuit? A parallel tuning circuit consists of capacitor and inductor in parallel, is shown in the figure below, that is in parallel circuits. In practice, some resistance R is always present with the coil. If an alternate voltage is applied across this parallel circuit, the frequency of oscillation will be that of the applied voltage. However, if the frequency of applied voltage is equal to the natural or resonant frequency of L circuit, then electrical resonance will occur. If the frequency of applied voltage is equal to the natural or resonant frequency of L circuit, that we can electrical resonance will occur. Under such condition, the impedance of tuning circuit becomes maximum and the line current is minimum during parallel. So parallel resonance, a parallel circuit contains reactive elements L and C, is resonant in an AC circuit if applied voltage and supply current are in phase, that is in step with when current and voltage. Resonance is said to occur. If this happens in parallel AC circuit, it is called parallel resonance. When the circuit power factor is unity, what we do in the XL balanced with XC, that we can get resonance frequency. That means XL balanced with XC means that is unity factor. That means applied voltage and supply current are in phase. So the phasor diagram of parallel circuit shown in the figure version 2. The coil current IL has two rectangular components via active component IL cos theta L and reactive component IL sin theta L. This parallel circuit will resonate when the circuit power factor is unity. This is possible only when the net reactive component of the circuit current is 0. So that means parallel resonance current in the capacitor minus of current in the inductor sine of theta L equal to 0. So that means IC equal to IL sine of L. Both supply current and applied voltage are in phase. So resonance in parallel circuit can be obtained by changing the supply frequency as some frequency F are called resonant frequency. IC equal to IL sine of theta L, and the resonance occurs. So when you see in the circuit, so when you see in this circuit, to analyze a parallel resonant circuit, so this is a parallel circuit. When it's shown in this figure, that's a parallel RLC circuit. So during parallel LC, it has one branch RL circuit, second branch IC circuit or XL circuit. So the common for both branches, our voltage for both common. So the net reactive for this circuit to determine. So first let's find the voltage and current relation. So in the first branch during R and L, voltage lead and current becomes lag, IL lag, that from 0 degree up to 90 degrees. So the nature of reactance of inductive current becomes lag voltage lead. In the second branch, that's only capacitor, so current lead voltage lagging by 90 degree. That's the nature of reactance of capacitor. So when you superimpose both, that means that is a phasor diagram for the x-axis is our voltage, the y-axis in the positive side is IC, in the negative side IL sine of theta. So that our resonant frequency that occurs during current becomes 0. So the total current we can get IL cos of theta. So that means the current during reactance of inductive becomes lag by theta. So by this means the phasor diagram of the relationship of our parallel circuit looks like this one. So during this time IC equal to IL sine of theta. From this equation we can analyze or we can get the resonant frequency. So let's simplify this equation. IC equal with IL sine of theta. So IC means simply Ohm's law. IC means voltage applied in the reactance of capacitor AC volt. So V over XC. The same IL means it has a resistor and also an inductor. So the voltage applied in this impedance circuit, because the summation of R and L circuit. So V over Z1, that's impedance circuit. The same, what does mean sine theta? According the phasor, the right angle triangle of the impedance, the diagram of impedance, that is XL and R. It has two components, reactive components, inductor and capacitors. So we get total impedance. So Z1 during this circuit, how can you get sine theta? Sine theta becomes opposite over hypotenuse, right angle triangle rule. So our opposite becomes XL, our hypotenuse becomes R. I mean Z1, sorry. So sine theta means XL over Z1. So when you simplified this circuit, simply V cancel by V, then XC XL equal to Z1 square. So XCL means 1 over 2 pi FL, or omega 1 over omega C multiplied with omega L. Omega means, if you remember, that's 2 pi F. That's simply principle, so you can substitute by this one. So equals Z1 square. So Z1 square from this right angle triangle, Z1 square becomes R square minus XL square. So Z1 becomes under root of R square minus XL square. So omega cancel it. So L over C, this becomes R square minus XL square. So XL square becomes L over C minus R square. So what does mean XL square, or reactance of inductive? So 2 pi FL square. This becomes L over C minus R square. So to determine the resonant frequency, F square becomes that under root of, because under this F square, let's see, F square, let's see, sorry, let's show you simply 2 pi F square that is of square is equal to 1 over 2 pi L over C minus R square. So FR, that means under root of this whole square. So 4 pi, 2 pi, that means 1 over 2 pi L under root of LC minus R square. So you can simplify it again, this circuits. So that we get resonant frequencies from the parallel circuits FR. When our R value is given, we can get by this equation, or we can simplify it again. Look, in this frequency at which parallel resonance occurs, reactive component of circuit current becomes 0 is called resonant frequency FR, when IC equal to IL sine theta of L. Now IL V over ZL sine theta XL over ZL, and IC V over X. Therefore, when simplified, V over X equal to V over ZL multiply with XL over ZL, V by V cancelled, XL X is equal to ZL square. So XL XC 1 over omega L over omega, omega by omega cancelled, ZL square. L square means R square plus XR square. So L over C becomes R square plus 2 pi FRL square, the whole square. When you move to this one, XL square, that means 2 pi FRL the whole square, L over C minus R square. So 2 pi FR under root of L minus R square. So FR 1 over 2 pi L under root of L over C minus R square. So for resonant frequency during parallel circuit, when included R, you can simplify this circuit to this one. Equation 2, if the correlation R is small, that is negligible, that we can use that in the previous what we do, XL balanced with XC, that we can get FR becomes 1 over 2 pi under root of LC. Third equation. So the resonant frequency will be inherited if R, L, and C are in Ohm, Henry, and Farad respectively. Note, if in the problem the value of R is given, the equation 2 should be used to find FR. If R is given, we can use this equation. However, if R is not given, then equation 3 may be used to find FR. So if you have no negligible FR, very small, we can use this equation. So this is how to get resonant frequency during parallel circuit, how to analyze this. So next we see the parameters of or characters of parallel tuning circuits.